So today we're going to keep talking about nanocrystal nucleation and growth mechanisms and um, what is known and what is not known about these kinds of reactions. This is my personal area of interest, and it's something that is not very well understood. There are many ideas and not a lot of good scientific evidence supporting um, mechanisms. And so I would say there's quite a bit of learning to be done and opportunities. Uh, Salvador is asking about the lectures posted. They should be posted. If they're not, then I need to go take a look at that after this. Thanks, Salvador. I'll make sure that they are up. Um, I'm surprised to hear that. I'll go follow through after this and make sure that's done. So as I was saying, nanocrystal nucleation and growth is an important topic and one where there's not a lot of deep chemical insight and a lot of opportunity uh, to to learn more and to develop a deeper, more rational approach to nanoparticle synthesis. So I wanted to review some of the things that we talked about last time. Um, you know, what is known is shown here. Generally speaking, in a nanocrystal synthesis, the sort of dominant mechanisms that you hear about are precursor conversion, where reagents added to the synthesis have to undergo some kind of a chemical reaction to produce the solute that then is in equilibrium with crystals. So prior to some kind of conversion reaction step that's irreversible, um, you don't have solute. And solute is formed by that conversion reaction step. And the kinetics of that dictate how fast the crystallization can go. In some cases, it's the rate limiting process, and others it's not rate limiting, but in many cases it will be rate limiting. And so the reactivity of the chemicals used in the synthesis matters. Once solutes are formed, they will supersaturate. They'll exceed the solubility limit, and a driving force for precipitation will cause them to nucleate. And we talked about nucleation kinetics last time and classical pictures about them and how they depend on the surface tension. And then once crystals are formed that are larger than the barrier to nucleation, those crystals can consume solutes. So solutes then have a choice of either forming a new crystal or attaching to an existing crystal. And then finally, when the solute concentration reaches steady state, where when the precursors are fully converted and all solutes have been formed, the solute concentration then reaches equilibrium or attempts to reach equilibrium with the crystals in the solution. And one of the mechanisms that turns on under those conditions is a process called Ostwald ripening. And that's a reaction where the monomers come on and off the crystals. So the crystals are in equilibrium with solutes. And because of the Gibbs-Thompson relationship, where a larger crystal is more thermodynamically stable, where a larger crystal is lower in energy than a small crystal, the small crystals will preferentially dissolve and the large crystals will preferentially grow. And this leads to a growth in the average size. It leads to a broadening of the size distribution, and the kinetics of which are all determined by the concentration of monomers in the solution, how soluble the material is. And so this Ostwald ripening process is a kind of a particle cannibalism, which you can see in this video here of these red droplets phase separating. Slowly you'll see small droplets disappearing and the larger ones growing. Occasionally you'll see two droplets fuse, an aggregation type of a mechanism. But sort of simple picture is the exchange of monomers as soluble units between the crystals. So we talked about how each of those processes map onto Lemaire's explanation for burst nucleation controlling the size distribution. So in a normal nanocrystal synthesis, where you have precursors that undergo slow conversion, you supersaturate the solution with kinetics that are determined by this conversion reaction rate constant or rate. And that process is slow, often compared to crystal forming steps. And what that means is that the solute concentration climbs steadily until you hit the critical concentration, the second phase of Lemaire's picture, where nucleation turns on. And then that process is very strongly dependent on the solute concentration. So it happens very rapidly. And then those particles begin to deplete the solution by growth. And that dropping solute concentration turns off the nucleation, and you enter the third phase, which is just consumption of supersaturated solutes by existing crystals and no more production of new crystals until the solutes are depleted and no more are formed. And then you reach a sort of quasi-equilibrium or steady state situation where the crystals can continue to grow by Ostwald ripening. So the important part about this mechanism for today's discussion is that the width of this nucleation phase is really the key aspect of this mechanism. Lemaire was borrowing the classical nucleation theory concept that nucleation turns on suddenly at this critical concentration, and that the kinetics of nucleation are very rapid above that concentration. And he said that the fluctuations in concentration at that critical limit will be small. Once you hit it, nucleation turns on. Once you drop below it, it turns off. And that effectively separates the nucleation from the growth phase and makes all crystals at one time early in the synthesis. And Tadao Sugimoto, borrowed this idea and really took it a lot further in his studies of silver chloride. And we talked about this nucleation mass balance that is a really important concept when you have slow production like this, where you can adjust the kinetics of the solute supply, either by a chemical reaction or, in Sugimoto's case, often it was just by the slow addition of the solute, actually separate silver and halogen ions being squirted in via 2 syringes. He could control the kinetics of the supersaturation and probe its effect on the nucleation. And he found this linear relationship between the kinetics of the solute production or solute supply, which is this symbol Q naught, and the number of crystals that form. Sugimoto explained this result using his mass balance equation. And so I've illustrated here. You can think about what happens to all the solutes during the nucleation phase. In this equation here, you have the solute supply, and this is expressed in volumetric units. Remember that Vm here is the molar volume. So you take the concentration per time, changing concentration per time, multiply by the size of each unit, and you get the change in the volume of material with time. And that's the solute supply. And he says all of that solute either goes to growing nuclei, some rate constant for growth, times the number of crystals in the pot, and the formation of new nuclei. And this is the volume of a nucleus, since this is in volumetric units, the change in the number of nuclei with time. That volume of material here is expressed this way. So you either grow nuclei or you form nuclei. All of the solute supplied goes to those 2 processes. And what Sugimoto realized was that if it's the case that nucleation has this critical dependence on concentration, once you hit that level, which is marked as a blue dashed line here in this figure, where this is the supersaturation ratio or concentration of solutes divided by the equilibrium concentration, which is 1 here. Equilibrium, when you divide the actual by the equilibrium, you're at 1. So this is the equilibrium concentration. These reactions get to supersaturation ratios of about 3.5 or so. So once you hit that level, nucleation turns on in very dramatic fashion, as proposed by the classical nucleation picture. And any new solutes that are generated by the solute supply at that point do not raise the concentration in solution, but instead cause nucleation, because nucleation turns on so incredibly steeply, you can't push the concentration any higher, and instead all monomers formed deposit on existing crystals. Okay, so at this critical limit, the solute concentration stops changing, and so the solutes must either make nuclei or stick to existing nuclei. And because of that, because this fact that the solute concentration is fixed or constant during the nucleation phase, it makes it possible to solve this nucleus growth part. This growth process here effectively becomes constant. Normally, growth is concentration dependent, but during the nucleation phase, although it is concentration dependent, the concentration is fixed because of this very steep turn-on phenomenon. And so that makes this growth rate constant here, or this growth rate a constant, and it makes it possible to solve this equation fairly simply and arrive at this, this relationship where the number of crystallites that are formed during the nucleation phase is proportional to the supply rate, or inversely proportional to the growth rate. Okay, so let's talk a little bit more about why that's the case. But the Sugimoto equation is a very nice example of how this solute supply rate and precursor conversion kinetics, the precursor reaction kinetics and solute supply rate dictate how the nucleation process happens. So in addition to the rate of the reaction controlling the number, the other very important aspect of this is how the growth rate influences the number. So I think I've said this enough times already, but this is the nucleation rate, so changing concentration with time versus the solute concentration. As the solute concentration approaches the critical concentration and then exceeds it, the nucleation rate turns on very steeply. And so because that's the case, the solute concentration can't go much beyond this critical limit. And if it does, it just, instead of pushing the concentration up, you just produce nuclei. Okay, so that was, as I said, Sugimoto's justification. So let's take a look here at this in a slightly different format, okay? So in a more graphical type of a relation. And this picture here where we have precursors reacting with one another to make solutes, and then solutes having a choice whether they make new nuclei or they stick to existing nuclei and grow them into larger crystals. This figure here helps you see that there's kind of a competition going on. So the objective is to consume the supersaturated solutes, right? We want to lower the solute concentration. And so, the only ways to do that are to make new crystals or attach to existing crystals. And there's a choice. There's sort of a competition between those two processes. So you can imagine how the growth rate constant, which might be proportional to the solute concentration, for example, and the concentration of crystals, the total amount of, or the probability with which this monomer attaches to this crystal is dependent on the number of those crystals, right? It's also dependent upon the mechanism by which the attachment process happens, okay? And so, the nucleation is going to be some kind of relationship that only depends on the solute concentration. This is an assembly of solutes in homogeneous solution. In our current mechanistic picture, we're just considering homogeneous nucleation. And so there's going to be some kind of concentration dependence. Maybe it's the classical concentration dependence, which is very steep. But there's no other concentration dependence. Whereas in growth, the total probability of solutes going in this direction is dependent on the number of crystals. Okay, and so during the nucleation phase of these reactions, the number of those crystals is going up. And so as nucleation is proceeding, the probability that solutes go to attaching to existing crystals is increasing. And eventually, the growth process completely overtakes the solute, and all solutes go to growth. Now, when does that happen? Okay, so at what stage does that happen? Well, that happens when the total consumption of solutes is faster than their production. So you supersaturate, you hit the critical concentration, at which point nucleation turns on. And then you start making crystals, and those crystals start competing for solutes. And eventually, the number of crystals is high enough that they outcompete the nucleation process entirely, and they begin to exceed the solute supply rate. And under those conditions, the solute concentration will drop. And that's when nucleation stops. Okay, so the growth process is kind of the process that dictates how long the nucleation phase happens. The faster the growth kinetics, the sooner the nucleation turns off, because growth is the thing that turns the concentration downward and below the critical concentration. Okay, so if a given crystal is really good at growth, if it's a fast growing crystal, then it'll shut off the nucleation process faster, because it takes fewer crystals to turn the concentration downward to outcompete the solute formation and outcompete the nucleation process. And of course, as the concentration goes up of crystals, that will also help to outcompete the production and the nucleation. Okay, so growth is this kind of, like, I call it the bailout mechanism. It's the escape path out of the nucleation phase. And so this relationship between the number of crystals and the growth rate constant makes a lot of sense. The faster this growth rate constant, the fewer crystals you need to escape the nucleation phase. If growth is really slow, you need a lot of crystals to consume all the solutes being formed. Okay, so Sugimoto's mass balance equation really lays that out very simply and solves that situation for a very ideal case where nucleation is an on-off function of concentration at this critical limit. Okay, so I'm going to show you, in addition to talking about growth mechanisms a little bit, I'm going to start showing you the kinds of reactions that people have studied with this sort of theoretical backdrop in mind. And my own group has put a lot of time into this, trying to demonstrate that these sorts of conditions apply in colloidal nanocrystal synthesis. And in particular, where we started was with a method that controls this precursor conversion rate. Okay, so precursor conversion, the reaction of these molecular starting materials, can dictate how many crystals form. And if you're making a mole of material and you change the number of crystals that you make from that mole, you change the size of the crystals that you get, right? So if you make a lot of crystals, at the end of the reaction, they'll turn out small. It's like a pie cut into pieces. The greater the number of pieces, the smaller the slices. And so we wanted to show that this reaction rate constant was important for controlling size and controlling number. And one of the platforms that we've developed for this purpose are these thio and selenourea reagents, or urea reagents. And these compounds are interesting because it's very easy to synthesize them. I haven't shown how, but you can make them a couple of different ways from commercial chemicals, especially the acyclic ones. These di and tri-substituted ureas can be made from isothiocyanates or isocyanides and amines in a sort of a click reaction. And the powerful thing about that is that, it becomes possible to make many different members of a library with different substitution patterns. And what we have shown is that their reactivity toward metal ions is very strongly dependent on that substitution pattern. And, we're talking about a factor of 1 billion or so in relative reactivity just by making these substitutions. So huge amounts of flexibility. Now, who needs a factor of 1 billion in reactivity? Well, it turns out that crystal growing is often done at different temperatures depending upon what the metal ions and surfactants are that you use to grow those crystals. And so some reagents work at high temperatures and others do not. Some reagents work well at low temperatures and others do not. And a lot of that has to do with uh, tuning the solute supply kinetics to match the crystallization half of the reaction. So um, to arrive at this situation diagrammed at the top where the precursor conversion kinetics matter. One of the model systems that my group has put a lot of effort into is the crystallization of lead chalcogenides. And I've shown an example of a lead sulfide synthesis done at about 120 degrees. Typically, these kinds of crystallizations work well between about 70 or 80 degrees and about 130 or 140 degrees. And so the dye-substituted compounds work very well under those conditions. And notice here, we're running this reaction with 1.2 equivalents of lead to sulfur, or sometimes it's actually 1.5 equivalents of lead to sulfur, because the final product is actually this mixture of lead sulfide and lead oleate. And you should expect that because that the metal carboxylate will bind this crystal as it grows, passivated surface, and provide a mechanism for attaching the surfactants. So the lead oleate starting material acts as both the reactant for making the lead sulfide and the ligand for the particle as it grows. So down in the bottom are kinetics that show us the formation of lead sulfide. And I'm not going to talk about this in depth, but the percent yield of lead sulfide can actually be measured by monitoring the absorption. And there's a variety of strategies to do that. But one of those is to just monitor the concentration of material at high energies, at high optical energies. So at 400 nanometers, the material doesn't have much dependence on the absorption spectrum is not strongly size dependent. Excuse me. Here we go. The extinction coefficient is not strongly size dependent. It's just proportional to the volume of material. So this is an energy where the E versus K diagram is not discrete, but kind of continuous. And it just looks like a bulk semiconductor. So you can monitor the amount of lead sulfide being formed by measuring the absorption of the solution at high energies. And you can see smooth curves here. And it turns out these curves fit single exponentials very well. And in this particular study, we're adjusting the para substituent here, this red X. And that red X is giving us giving us a way to control the kinetics. So this methoxy substituted compound in purple is much slower to produce lead sulfide than this fluorinated substituent here in red or orange. Um, and so these curves here actually turns out they fit single exponentials pretty well, and we can use that exponential fit to estimate the relative reactivity. And we can make a Hammett plot, which is something out of physical organic chemistry that we're not going to spend time talking about. But it tells us that the kinetics of these reactions are very well behaved, and that all of these nanocrystal forming syntheses are following the same conversion mechanism. So we have good, reliable chemistry. The more important plot here is shown on the right, where we take these rate constants that are extracted by fitting those curves to a single exponential, and we plot them versus the concentration of crystals. So further to the right is a faster reaction and a higher concentration of crystals. And you can see a steady increase in the number of crystals with time, with reactivity. Faster reacting substrates give you more particles at the end of the day than slower reacting ones do. And that's consistent with this sort of Sugimoto picture, but you'll notice that this curve does not fit a straight line very well. It maybe in this region it's quasi-linear or something, but doesn't really seem to exactly fit the Sugimoto condition that we talked about before. Regardless, for the time being, the other thing to note here is the diameter of the crystals that come out of the synthesis after complete precursor conversion. So this is the diameter at the end of the reaction. And as you might expect, a higher concentration gives you a smaller size than a lower concentration. So we verified in these kinds of conditions that the conversion reaction rate constant to the precursor is related to the final size of the crystal at the end of the synthesis. Some of you might be wondering, what about Ostwald ripening? Ostwald ripening would mar this result, or maybe obscure or flatten this curve. And it turns out under these conditions, the solubility is so low that the crystals don't exchange monomers very rapidly, and the kinetics of Ostwald ripening are too low to be important. Okay, now we've also demonstrated the same principle using a class of selenium-containing ureas. And generally speaking, carbon-selenium bonds are weaker than carbon-sulfur bonds. And so you need to use precursors that have 3 substituents on the nitrogen instead of 2 to get the kinetics right. Okay, so you want the kinetics to happen slowly or at just the right speed. And the tri-substituted selenoureas are the right sort of reactivity for that purpose. And you see the same kind of relationship between the rate constant for the conversion reaction and the number of crystals that you make, or the concentration of crystals that you make. And one of the sort of cool technological advantages of a method like this is that if you want to get a particular size, rather than stopping the reaction by cooling it down, what you do is you just change the compound and you change the number of crystals and you drive all of the starting materials to products. In the case where you stop the reaction and cool it down, you actually throw away a bunch of material, and you're left separating the crystals from all this lead oleate and unreactive starting material. And that has caused a lot of problems in the community. This method of controlling size is a better method because it uses up all of the added lead and sulfur, and it allows you to dictate the amount of excess lead that's present for passivating the crystals, and it simplifies the purification procedures. And shown on the right here are a bunch of different nanocrystals made with different compounds that have a compound number. Each of these different molecules has a different reactivity, and you can see we get a very smooth and finely graded control over the size just by changing the substitution pattern. Okay, so the other thing about this reaction that turns out to be really great for mechanistic studies is that the size distributions are really narrow. So the peaks that you're looking at here, these are the lowest energy excitonic transitions in the semiconductor. And you can see in the lead chalcogenides, they're really separated from the next highest absorption. So take this one, for example. As you go out to large sizes and long wavelengths, notice how far this excitonic transition is from this one and that one. Those are big spacings. And you know, that those spacings, the visibility of them is partly related to this line width. Okay, so the line width of these features is really narrow, and that's really powerful for doing model studies. So I thought I had, we'll come back to that, I guess. Unfortunately, I don't have time to take you through all of these characterization techniques in depth, but my group has been using these conditions to study the nucleation kinetics and to try and test the hypothesis that classical nucleation theory has put forward, that the nucleation has this very strong concentration dependence above a critical threshold. You know, basically we want to put Sugimoto's theory and classical nucleation theory to the test. And we're using a couple of approaches to study that issue. You've seen this absorption spectroscopy method now. That's one method of measuring the production of crystals. Two others involve X-ray scattering techniques. This is something called pair distribution function analysis. And it's a sort of wiggly looking thing that may be very unfamiliar to you. But just sort of briefly, I'll say that this is each one of the peaks that you see here is a regular distance in this sample. So it's a sort of a histogram of distances in the material. And with time here, we're going from blue to green to yellow to red to black. Crystals are forming, and so you see regular spacings in this pattern here that can be used to extract things like the crystal structure, i.e. rock salt, or the particle size. Now, another technique that we make a lot of use of is called small angle X-ray scattering. Remember that the scattering angle is related to the size of the object that's scattering the X-rays. So if you're doing an X-ray crystal structure, for example, the two atoms that are, say, 1 or 2 or 3 angstroms apart from one another will scatter X-rays at a very high angle. But if you're talking about something that's large, like a nanoparticle, that object will have spacings on the order of 5 nanometers or 50 angstroms apart. And that large spacing gives rise to a smaller scattering angle. And it gives you this kind of a curve here. This curve is a small angle X-ray scattering curve, and it can be used to extract the size of the object that is scattering the X-rays. And so you take one of these curves during a synthesis, and you can measure the amount of material that's scattering X-rays by just how much X-ray gets scattered off of the material. The more stuff you have, the more you scatter. So you can measure the yield of material from the intensity of the scattered light. And then the shape of the curve tells you about how big the crystals are. And it turns out it has this sort of wiggling pattern here, and those wiggles are related to the shape and to the size of the object. And you know, because our crystals have very, very narrow size distributions, you get these wonderful clean wiggles. If you had a mixture of different sizes, you wouldn't see wiggles at all. You'd see some sort of a smear, but not in our model system. So anyway, one of the things we've done is to take SAX, small angle X-ray scattering curves during crystal formation very steadily over time. So this is a very sparse data set. Actually, there's many more curves than what I'm than what's being shown here. And those curves are increasing. The signal is increasing in intensity with time, and the wiggles are shifting inward like this, telling you that crystals are growing to large sizes and that the number of them is going up. So you can fit all of these curves, and from that extract the concentration of crystals that are forming and the size of those crystals versus time. Okay, and that allows you to actually monitor nucleation kinetics directly. Okay, so here we're watching the number of crystals increase over time, and very directly using this technique. And so one of the things you might notice here is that, or you hopefully would notice here, is that the nucleation process in the synthesis is very long. It's drawn out. So something like half of the reaction, uh, more than half of the reaction or so, you're nucleating crystals. So this is not what Lemaire predicted. Lemaire said to get a narrow size distribution, the crystals should all be born at once. And they should not be slowly produced. They have to be horses have to be let out of the gate all at the same time. But instead, what we see here is that the crystals are forming very slowly over the synthesis. Okay. And so that is uh, a result that very clearly contradicts the Lemaire principle. And it also does not fit with Sugimoto's picture of how nucleation happens under these conditions. Okay, so to explain this, I should say it's not very straightforward to explain this result with existing mechanisms. So I'm going to show you one possible alternative to this. But first, I want to say something about the line widths and the size distribution in these samples. And basically, what I'll tell you first off is that the size distributions are almost perfect, meaning that under our conditions, the crystals and many other people's conditions, the crystals that are produced have a few percent, maybe 1 to 3 or 1 to 5% size distribution. Often, the way people will measure this or estimate the size distribution is by looking at the width of the excitonic feature. Right? The energy of these excitonic features is size dependent, and if you have a distribution of sizes, you will have a distribution of energies. And so people often use that width as a measurement of the size, but it turns out that each individual size also has an intrinsic kind of a width to it. And so you're actually taking the sum of many Gaussians or Lorentzian shapes to get this width. And it turns out that the width that you see in this spectrum here in red and the ones I showed you earlier is almost all intrinsic width and not width caused by the distribution in size. And that's actually plotted here on the right. The black points are the intrinsic width, and the yellow and red points are the width of the ensemble. The difference between these two curves is the total amount of broadening that's caused by the size distribution. And that amount is just a couple of percent over the entire sample size. The other thing, so I should have taken a little more care to explain what you're looking at here. This axis is the energy of this transition. So wavelength space here, energy units here. So as you go from low energy to high energy, the spacing of the 1s to 1s electron to hole transition, or the first excitonic transition, um, uh, uh, as you go from low energy to high energy, you're going from large crystals to small crystals. Okay, FWHM is the full width half max of this peak. And as you go from large crystals to small crystals, the width of that peak actually goes up. Okay, and so the width, the intrinsic width goes up, as does the ensemble width. So, there's a couple of things to learn from this graph. One of which is that the intrinsic width of the spectrum is size dependent. And the other is that in these samples and many other people's samples, the widths that you see are dominated by this intrinsic broadening and have very little broadening associated with the size distribution. And this is not something that many people are aware of. I guess maybe an increasing number of people are aware of this, but you'll see many papers on this topic that suggest otherwise. Okay, so just maybe FYI on that. All right, so we have a little bit of a quandary here. I'm telling you that there's no size distribution, or that the size distribution is vanishingly small, and yet we see this very slow and steady nucleation process, not what Lemaire predicted. Okay, and so an open question in this area is, how do you resolve that? And we'll talk about a number of ways that you can resolve that going forward. But one of them is a process called size distribution focusing. And I'm going to probably return to this next time, but I'm going to just sort of throw it out there for now to kind of um, help you understand how this might possibly work. So a size distribution can do something called focusing, and focusing happens when you have a broad collection of sizes that somehow becomes sharper over time. Okay, and the only proposed explanation for this, or I guess one of two proposed explanations for size distribution focusing, comes from Howard Rice, who was a student of Victor Lemaire's. Rice said that diffusion limitations on the growth process can give rise to a size-dependent growth, right? Where small crystallites actually consume solutes faster than large crystallites do. Okay, and when you have that kind of situation, the size distribution will narrow. The small guys who are a long way away from the big ones will catch up because they grow faster. Okay, and there's this relationship between the growth rate and the critical radius that we're going to come back to that can give rise to narrowing of the distribution at high supersaturations and broadening of the distribution at low supersaturations. And these two conditions actually relate to Oswald ripening. Okay, so we'll come back to this, but just for the time being, size distribution focusing is one possible explanation for why the distributions turn out narrow, especially if Lemaire is wrong. Okay, we need something like this to explain why the distributions are so narrow at the end of the synthesis. So let's talk a little bit about what these sort of growth processes are like, and introduce you to the sort of a few alternatives here. Okay, so one of them is where growth kinetics are limited by diffusion. So what does that mean exactly? On the left here, I've drawn a nanocrystal with a given radius, surrounded by what's called a diffusion sphere. And the diffusion sphere separates the transition from a region where the monomer concentration is dropping as you get closer to the nanoparticle, from a region where that's basically the bulk solution, at the solution concentration. So under diffusion limited kinetics, the monomers can't get to the particle fast enough. And close to the particle surface, there's actually a lower concentration of monomers than there is out in bulk solution. So this sets up a concentration gradient, and it sets up and you get this diffusion sphere. So the width of that sphere is labeled delta. The radius of this particle is labeled r, and then I've shown here how the concentrations of solutes in the solution is plotted, again showing you the width of the diffusion sphere. So this is the solid here, and this is solution. This boundary defines that separation. And so there's the bulk concentration, and the bulk concentration is above the solubility limit of the material. Okay, so this is a supersaturated solution. Remember, the Gibbs-Thompson equation tells you the concentration of solutes for the equilibrium concentration of solutes for a given radius. The solubility of the material is size dependent. If you have a large object, then solubility is equal to the bulk solubility, which is this C infinity here. I should have used the same nomenclature. This is the bulk solubility. And the smaller the crystal gets, the more soluble it becomes. Oh, let's see here. I'm glad I didn't use the, sorry, this is the solubility of the bulk material. This is the concentration of monomers in the solution. And so this is supersaturated. It's above this limit. And this concentration is going to be higher than the solubility limit of the crystal. And it's modified by the surface tension and the radius. So a small crystallite is more soluble and will be in equilibrium with a higher concentration of solutes than a large one. Okay, so under conditions where the solution is at a concentration that's higher than the Gibbs-Thompson solubility, you're supersaturated, and when the growth is limited by the kinetics of diffusion, what you'll get is this decreasing concentration of solute as you approach the particle surface until you reach the particle surface and this CI concentration, so the actual concentration at the growing crystal. Okay, so diffusion limitations say that there's this monomer depletion that happens because of this, because of the transport of monomers to the crystal being slower than their consumption by the crystal. So you can express the growth rate of that crystal in terms of the flux of monomers passing through reaching the particle surface per unit time, or more generally as the flux of monomers passing through a sphere with radius x. Okay, so this is Fick's first law of diffusion. So this is moles per liter per unit area per time, and this rate of growth is then the surface area of the sphere times the diffusion coefficient of the monomers in the solution times the change in concentration as a function of distance. Okay, so this is this is expressed as a concentration per unit area. So you can also express things as a linear growth rate if you want, where now we're referring to the change in the radius of the particle with time rather than the flow of monomers through a sphere with time. So the change in the radius with time turns out to be this value normalized to the surface area. So if you take all of the monomers flowing to the crystal and you divide by the surface area, you can get the change in the radius with time after you include the volume of the units that are attaching. So this volumetric or the molar volume is included there to do that conversion to geometry instead of number of units. So you can integrate Fick's first law from the edge of the crystal to the edge of the diffusion sphere to get a growth rate. Whoops. Let's see here. To get a growth rate here expressed in this way, and this this growth rate is basically taking the concentration in the bulk minus the concentration at the surface. So this total amount of monomer here is the excess monomer above the monomer concentration at the particle surface, and multiplying it by this these terms here. So this is what's known as the diffusion controlled growth rate that just comes from Fick's first law. So so let's consider this in a little bit more depth. So we have, think about this as a two-step process, and we're going to consider the attachment rate constant here in this case. So we have diffusion of monomers to the growing crystal, where they're dropping in concentration, and then they hit the surface at some concentration CI, and then they undergo an attachment reaction. Okay, and so there are cases where diffusion limitations are not important at all, and the kinetics are really dominated by the kinetics of attachment to the growing crystal. Okay, and you still have this linear growth rate in the surface attachment limited case, but now you have some attachment rate constant K multiplied by the area of the crystal and the concentration of solutes that are available for growth. This concentration is really the CI minus the solubility of the crystal. Okay, so this is the total amount. You can think about this as the concentration of solutes that is in excess of the solubility times the area times the attachment rate constant. And so, um, so this is another limiting case. Okay, now during a crystal growth process, these two things kind of become equal to one another. Let me see how I'm doing on time here. Excuse me. Sorry. Okay, got a few minutes left. So during crystal growth, these two processes become equal to each other. So they're both in, they at steady state, the rate of consumption and the rate of diffusion end up becoming equal. And so you can set these two um, uh, uh, growth rate equations equal to one another, the surface attachment one and the diffusion one here, and move things around and get down to a pretty simple equation where the concentration of the amount of solutes that are in excess of the solubility and the amount of solute that's depleted by diffusion, this ratio is just the ratio of the diffusivity of the monomers over the attachment rate constant. Okay, so pretty simple kind of a relationship. And I've shown this to you here to help you understand that the that these are sort of competing processes again, right? There's the attachment and there's the diffusion. There's going to be some balance between those two in a real crystal growing situation. And it can be all the way on one side or all the way on the other side and somewhere in between. Okay, and that's going to fluctuate. That's going to change the concentration of solutes at the surface as the crystal grows. Now, let's consider two limiting cases, and we've already talked about them, but to help drive this idea home. So a case where growth is entirely controlled by the diffusion process. This is the case where the diffusion rate, the diffusivity of the monomers is really, really low. Let's say the solution is, honey with a very high viscosity. Diffusivity is really, really low, and so the monomers they take forever to get to the crystal surface, and that process is so much slower than any kind of attachment that it's really all about diffusivity and has nothing to do with the attachment. As soon as they reach the crystal surface, for all practical purposes, they attach. Okay, so under those conditions, you end up with a situation like this where the monomer concentration drops and drops and drops until it reaches the solubility of the crystal. So the CI comes all the way down to the solubility. CI cannot drop below that value. Uh, um, in essence, this crystal is in equilibrium with the solute concentration right at its surface. Okay, so under those conditions, you get a very large diffusion sphere. And you can simplify the growth rate constant into these geometric terms and the diffusivity, and then this difference between the bulk concentration and the solubility. Okay, that spacing there. So in the previous instance, this was just Ci, and I've replaced it with Cr. And so if you take the linear growth rate and set those two guys equal to each other, you end up with a linear growth rate that depends on the diffusivity. It depends upon the solubility of the crystals and the bulk concentration, but it also depends upon radius. Okay, and this is really important because what this is saying is that under diffusion limited growth, the growth rate constant is size dependent. Okay, so when you have diffusion limitations, you end up with a mechanism of size distribution focusing. So small crystallites will have a greater linear growth rate than large crystallites under diffusion limited conditions. Okay, there are a couple of assumptions here. One is that the CR of the small and the large isn't dramatically different. Now, of course, the solute concentration is size dependent, so this is not entirely true, and that would actually dampen size distribution focusing to some extent. But in any case, Rice pointed this out, Howard Rice, that under diffusion limitations, it's possible to get into a situation where growth kinetics are limited by or are influenced by mass transport, and they become size dependent. All right, so let's consider the other case now. This is the case where you have surface attachment controlled growth. And so this is where diffusivity of the monomers is really fast, but they, at least compared to their attachment. So the monomers reach the crystal surface and they're kind of rejected because attachment is really slow. There's some kind of barrier to attachment. And, if you consider these mass transport issues, under those conditions, you'll find limited or no diffusion sphere, okay? So the bulk concentration will actually be equal to the concentration at the surface of the particle. There's no depletion because monomers can diffuse as fast as they need to, and really the problem is their attachment. So you don't get any depletion of monomers near the particle surface, and as a result, these diffusion issues are unimportant. Okay, so under those conditions, as we've said, this is really about how much solute is present over the solubility of the crystal. That's the concentration available for growth times the area and the growth rate constant. Okay, and then the linear growth rate under those conditions is just this G times these geometric terms, and you end up with something that's really all about the concentration and the rate constant for attachment. Notice no radius dependent term here. Okay, this is all about attachment kinetics. It is radius independent. So according to Rice, when you have these surface attachment limitations, you don't get any kind of reason why a small or a large particle would have different growth kinetics. Now, this is making some pretty big assumptions about, small and large crystals, and I don't think that this is true at very small sizes. And next time I'm going to walk you through some examples of how that's the case, and I'm going to also show you a little bit more about how this size distribution focusing curve relates to this diffusion limited case, but also how it relates to Oswald ripening, and talk about how that's relevant to size distribution focusing.